Hey folks, this is the third video in a multi-part series of short videos leading to the concept of the tensor product in linear algebra. In prior videos, we looked at the quotient space and the free space from a universal point of view, both to better understand those objects since they'll be useful to us later, and to get more comfortable with universal properties. In this video, we're finally going to tackle the tensor product itself. We'll also cover some of the biggest confusions and biggest mistakes students make with the tensor product and how to avoid them. Now let's get started. We first discuss the concept of bilinearity, which is central to the tensor product. Let u, v, and w be vector spaces over a field f. A function f from the set u times v to w, viewed as a function of two inputs, is bilinear if the induced functions obtained by fixing one input are linear maps. Here we use the dash symbol to denote an input that is not fixed. We call f a bilinear map, and in the special case that w is the field f, a bilinear form. There are two important things to note about this definition. First, it does not involve the direct product vector space u times v in any way. That is, it does not involve sums or scalar multiples of pairs. U times v here is just the Cartesian product set, that's it. Second, the image of f is not in general a subspace of w, only a subset. These are probably the two biggest confusions about bilinear maps that students have, so keep these things in mind as we proceed. Bilinear maps are everywhere in linear algebra. For example, scalar multiplication of vectors in a vector space is bilinear. This follows directly from the vector space axioms. In R3, the familiar dot and cross products are bilinear. The cross product has some other weird properties which I cover in detail in another video on this channel, but bilinearity is a very natural one. More generally than the dot product, the inner product in any real inner product space is bilinear. And not to be left out, the inner product in any complex inner product space is also bilinear, provided that we replace one copy of the space with its conjugate space, denoted here with a bar. The conjugate space has the same underlying addition, but scalar multiplication is defined using complex conjugation. If we don't use a conjugate space, then the complex inner product is not bilinear. More generally than the cross product, the exterior product or wedge product on any vector space is bilinear. This product has many applications in mathematics and physics. For instance, it leads to a very elegant treatment of determinants in linear algebra, which I covered in another video on this channel. For a final example, let LVW denote the vector space of linear maps from V to W, where addition and scalar multiplication of maps is defined pointwise. Then the evaluation map, which sends a linear map and an input vector to the corresponding output vector, is bilinear. This follows directly from linearity together with the definition of addition and scalar multiplication of maps. In particular, taking W to be the field f, it follows that the scalar product between a vector space and its dual space is bilinear. This scalar product is central to the study of duality in linear algebra, which I cover in depth in another video. Besides helping to plug my other videos on this channel, these examples should hopefully help convince you that bilinearity is an important concept. From the prior videos in this series, you should hopefully also be primed for a natural question at this point. Is there a universal bilinear map on the set u times v, from which all others can be obtained in a natural way? If so, it would be worthwhile for us to study it, because by doing so we would fully understand bilinearity on that set. What would such a bilinear map be? From our experience with universal properties at this point, we know that it would be a bilinear map, let's call it T, from u times v to some vector space T over f. And for any bilinear map f from u times v to any vector space W over f, there should be a linear map phi from T to W, which allows us to obtain f from the map T through composition. Here's what that looks like in a diagram. As in the other universal properties we've seen, the induced map phi should be unique. This is the universal property for the map T. My hope is that after seeing the universal properties for the quotient space and the free space in prior videos, this doesn't seem like abstract nonsense, but a natural idea for studying bilinearity. Right away we can read an important fact off of this diagram. The map T need not be surjective. As we mentioned, its image need not even be a subspace. However, since phi is uniquely determined, the image of the map T must span the entire space T. If it didn't, then there could be multiple maps phi making this diagram commute, which are defined differently on a subspace supplementary to the span. This fact will be useful shortly. Now, so far we don't know whether any such universal bilinear map T exists, but let's suppose for the moment that one does. We write it using the tensor symbol and call it a tensor product. We also write the space T as U tensor V and call it a tensor product space, and call its elements tensors. So we've finally arrived. This is a tensor product from the universal point of view. However, in introducing this notation and terminology, I need to immediately address one of the biggest confusions students have about this. Since this tensor product is universal, it's unique up to isomorphism. In fact, we know from the prior videos in this series that any universal object is unique up to isomorphism. However, in general, this tensor product is not unique. That is, in general, there are multiple ways to define a tensor product on U and V, which all satisfy the same universal property, but which look very different. Many students just learn one particular definition or other and think that the tensor product notation and terminology always refer to that particular definition, leading to much confusion. Don't be one of those students. Instead, embrace the universal point of view and hold two things in your mind at the same time. In general, there are multiple concrete instances of the tensor product of two given sets, but they're all isomorphic because they all satisfy the same abstract universal property. When we say a tensor product, we're usually referring to a particular instance. When we say the tensor product, we're usually implicitly referring to a whole equivalence class under isomorphism. The tensor symbol may be used in either case. With all of that said, let's continue our study. Bilinearity of the tensor product means that these relations always hold in the tensor product space. The first equation is linearity in the left input, and the second equation is linearity in the right input. Importantly, in general, not every tensor in the tensor product space is of the form U tensor V for vectors U and V. That's just because the tensor product map need not be surjective. Such tensors are very special and are called decomposable. Assuming that every tensor is decomposable is one of the biggest mistakes that students make. Don't do it. What is true is that every tensor is a sum of decomposable tensors like this. That's just because, as we already observed, the image of the tensor product map must span the entire tensor product space, and scalar coefficients in a linear combination of decomposable tensors can always be absorbed since the tensor product map is bilinear. However, it's important to note that this representation of a tensor is not in general unique, even for decomposable tensors. This is another huge mistake that students make. They'll try to define a function of a tensor using the vectors in such a representation, but the function isn't well defined because the representation of the tensor isn't unique. Again, don't do it, folks. The right way to define functions of tensors is using the universal property. In the new notation, it says that if f from u times v to w is an arbitrary bilinear map, there's a unique linear map phi from u tensor v to w, which maps the decomposable tensor u tensor v to f of uv. Here's the diagram. Importantly, the map phi is guaranteed to be well defined by the universal property. It's also uniquely determined by its action on decomposable tensors. Notice that the universal property allows us to factor out the purely bilinear part of f into the tensor product. The tensor product is bilinear and nothing more, and everything else that f does is carried out by the linear map phi. Another way to think about this is that the tensor product allows us to reduce a bilinear map to a linear map, or to exchange a bilinear map for a linear map. This localizes all of the complexity of bilinearity into the tensor product, where we can study it once and for all, separately from the induced linear maps, which are simpler. This is the great power and utility of the tensor product. At the risk of repeating myself, I want to warn again that it does not make any sense to try to define a linear map on decomposable tensors using a function that is not bilinear on the vectors. Such a function will not be well defined in general, let alone linear. So please avoid this. Okay, with warnings out of the way, let's look at some examples. First, scalar multiplication of vectors in a vector space is a tensor product. We can show directly that it satisfies the universal property. Given a function f from the set f times v to w, which is bilinear, we can define a linear map phi from v to w by phi of v equals f of 1v. This is linear since f is linear in its right input. Then if we look at f of alpha v, we see that it equals alpha times f of 1v since f is linear in its left input, which equals alpha times phi of v by definition of phi, which equals phi of alpha times v since phi is linear. This shows that f factors through scalar multiplication in v via phi. Moreover, the map phi is unique, satisfying this equation. Indeed, if we take alpha equal to 1 in this equation, we get the definition of phi that we started with. Therefore, the tensor product space f tensor v is just v when we take the tensor product map to be scalar multiplication in v. So every vector space is already a tensor product space. This example is very simple, but thinking about it actually helps us develop intuition for the tensor product in general. For instance, if vectors v1 through vk are linearly independent in V, and the sum u1 tensor v1 plus through uk tensor vk equals 0 in the tensor product space, then the u's must all be 0 in U. In particular, non-zero vectors have non-zero tensor product. When the tensor product is scalar multiplication in V, this is immediate from the definition of linear independence. So we can think of this result as generalizing the consequence of linear independence from scalar multiplication to arbitrary tensor products. The idea of the proof is to show that the u's are 0 by showing that they're 0 under any measurement by any linear functional. For f an arbitrary linear functional in the dual space of U, notice that the map from U times V to V, which sends the pair uv to the vector f of U times V, is bilinear. That's just because f is linear and scalar multiplication is bilinear. So it induces a linear map phi from the tensor product space U tensor V to V. Now, 0 is equal to phi of the sum, since the sum is 0 by assumption. By linearity of phi, that equals the sum of phi applied to the decomposable tensors. By definition of phi, that equals the linear combination in V seen here, where the linear functional f appears in the coefficients. Now, since the v's are linearly independent by assumption, it follows that those coefficients are all 0. And since f was arbitrary, it follows that the u's are all 0, as claimed. Isn't that a slick proof? Notice how the map phi reduces the problem from the general tensor product space U tensor V to the specific tensor product space F tensor V, where, as we noted, the result is immediate. This result gives us more insight into what is and is not a tensor product. For example, in R3, non-zero orthogonal vectors have 0 dot product, but non-zero tensor product. So the dot product is not a tensor product. Similarly, the cross product of a non-zero vector with itself is 0, while the corresponding tensor product is non-zero. So the cross product is not a tensor product. Intuitively, this all makes sense, because the dot product and the cross product satisfy other relations besides just bilinearity, so they're not universal. Similar reasoning applies to other bilinear maps that we've seen. In summary, at this point we've seen that a tensor product is a universal bilinear map. We've looked at some examples and we've developed some intuition. But how do we know that a tensor product always exists in general for two arbitrary vector spaces? In the next video, we'll prove this and gain deeper insight into the tensor product. Stay tuned.